Hi, my name is Ivey Rao, and I'll be presenting on my final project for Pivotport Inc.'s Summer 2024 internship, with special thanks to my supervisors, Rajiv Mistry and Jonathan Ortega. Here's an overview of the presentation itself. I will be giving a brief introduction to our project, go over our dataset, methodology, results, challenges, conclusions of future work, as well as my key takeaways from this project and the internship as a whole. Here's a brief introduction to our project. Our goal was to implement a quantum classification algorithm to analyze engine fault data for improved accuracy or training time. The problem we aimed to solve was classifying a large dataset of engine faults into categories indicating the presence and the type of the fault, which required a robust dataset with relevant engine features, quantum computing tools, and guidance on implementing quantum algorithms. We chose to use a quantum neural network, or QNN, with the IonQ quantum simulator and compare our results with a classical support vector classifier, or SVC. The execution plan involved pre-processing the data, training both of our models, optimizing them, and comparing their performance. The dataset that we ended up choosing is from an IEEE paper focusing on engine features and fault classification. It contains almost 60,000 snapshots of 14 engine features structured in a COC format. We normalize the values between 0 and 1 using min-max scalar to ensure a consistent scale for all of the features, which is important for improving our model's performance and convergence. Here's a figure taken directly from the paper itself that showcases their data collection process. First, they had a car stationed in their workspace. They had multiple sensors that would measure the features of the engine as it ran, such as the RPM, the speed, or the quantity of hydrocarbons emitted by the engine itself. Then they would induce a failure, and then they would take measurements of those features in the moment that the failure was induced. They would do an integrity check and then add the data into the dataset. Here's a preview of the dataset as a whole. As we can see here in the top row, those are the features that they are keeping track of as they induce engine failures. And on the very left, it shows whether or not an engine failure has been induced in the specific snapshot of time that these measurements were taken. Regarding our choice of algorithm for this classification problem, we chose to use a QNN due to its potential for reduced training times and higher accuracy. The original paper recommended a classical neural network due to less chance for overfitting and greater accuracy than many of the other architectures that they tested that we'll see on the next slide. Although the K-nearest neighbors test, or KNN, had a higher overall accuracy, we ended up choosing a neural network after considering the overfitting potential of the KNN that they mentioned. Our methodology involved comparing the performance of the QNN to a classical SVC. This comparison helped us to evaluate the benefits of using a quantum approach for this specific problem. And here's the table from the paper showcasing the stats for each of the classifiers. And as we can see here, the KNN's accuracy is indeed higher than the neural network, but the overfitting potential that they mentioned in the paper for the KNN was the reason why we decided to go with a neural network instead. Here I'll be describing the architecture of our QNN. Our QNN leverages quantum circuits for complex data representation that would not be possible classically. The QNN architecture includes multiple layers of these parameterized quantum gates to encode and transform the input data. We use the COV-YLA optimizer with a maximum of 10 iterations to optimize the parameters of the QNN, enhancing its performance by minimizing classification error. Here's an overview of the implementation of our project. Our project was run on VS Code on a virtual machine, or VM. We pre-processed the dataset by normalizing features between 0 and 1 using the min-max scalar. Then, we set up the Jupyter Notebook environment and chose the IonQ quantum simulator as the provider. We trained a classical SVC as the baseline model. Then, we created a VQC using quantum circuits. We optimized the QNN parameters with the COV-YLA and ran it with the IonQ simulator. Then, we implemented a callback function to monitor and fine-tune the training, and then compared the performance of the VQC and the classical SVC. And here's our results table. As we can see here, the classical models did outperform the quantum models in terms of accuracy, and the bottom row is missing, but this will be explained on the next slide. Throughout the course of this project, we came across several challenges. Our inability to increase the sample size from 10 to 2500, as seen on the previous slide, while still completing the run, resulted in accuracy issues and non-convergence. VM shutdowns restricted the ability to run larger sample sizes and iterations. Limited computational as well as time resources hindered our full exploration of the quantum simulator and effective QNNand training. The conclusions that we drew from this project was that feature reduction was absolutely necessary for streamlining the machine learning process and enhancing overall efficiency. Access to more powerful computational resources and extended timeframes would greatly optimize our network's performance. Some next steps would be to apply advanced feature reduction techniques to simplify our dataset and improve our model's efficiency, as well as secure the additional time and computational resources that would allow us to fully harness the potential of our quantum network. And finally, here are my key takeaways from this project and internship as a whole. First, quantum computing's inherent noisiness and hardware limitations have impacted our accuracy and experimental scope. I also gained extensive knowledge of quantum computing mechanics, programming, and hardware. I enhanced my own machine learning expertise, transitioning from my purely academic research background to more practical industry applications. I also learned why QNNs are preferred for certain types of classification problems due to their potential for reduced training time and higher accuracy, which, as stated, we hope to explore in the future. Thank you so much once again to Rajiv and Jonathan for having me on their team this summer.